So, for the most part of human history, light was thought to be a wave, and it's still believed to be a wave most of the times. What we actually see is that sometimes light behaves like a wave, sometimes light behaves like a particle. So, why was it thought to be a wave? Uh, for example, always uh, waves refract, and we know that light refracts. On the other hand, a particle, if you throw a pebble on water, you don't see this change of angle. You see a more curved trajectory. So in this case, light is behaving like a wave. The same way, light diffracts. So if you throw a beam of light through a small slit, you will see this kind of pattern that is typical of waves. If you threw a beam of particles, you would see a completely different pattern. So again, in terms of diffraction, light is behaving like a wave. And also in terms of interference, if you make two waves impact, you're going to see an interference pattern that light shows. On the other hand, if you make two particles collide, you're going to see a collision that does not look like the interference pattern. So it was because of all these behaviors that we always thought that light was a wave. So currently, we're not going to talk about it in this way, but what light is really understood today is using the Maxwell equations that say that, and these are the Maxwell equations, some of them, in which light is actually an oscillating electric field perpendicular to an oscillating magnetic field. This description is beyond the scope of this course, but I thought I should bring it up just in case you take physics or you have taken physics. So what we're going to see here, the kind of description that we will use here is a much simpler version of the actual description of treating light as a wave. So let's go back to the basics. What kind of properties can we associate to light if light is a wave? If you think of light as a wave, one of the most important properties is, one, the amplitude, which is the height of that wave, and the wavelength, that is from peak to peak. What is the length of this wave? So just think of it like in the ocean, the wavelength of light in this case is constant and is measured by the letter lambda. And it's in SI units, is used in meters. So, however, what light is not only this wave that propagates in space, it also propagates in time. What does that mean? It means that if you put someone in here and riding the wave, you would see that someone to go up and down. You would see this person as the wave progresses going up and down. So light is not only a wave that propagates in space, it also propagates in time. So this means that there is, from peak to peak, there is a magnitude that is called a period, which is the time that it takes to go from peak to peak. And this period is in SI units in seconds. So take home message, light is a wave that moves in space and time. We will use the wavelength and the period to characterize the displacement on space and on time respectively. Now there are other properties such as the wave number that you may be familiar from infrared spectroscopy, in which the wave number is only the inverse of the wavelength, so it's a property of space, and its very definition is the number of cycles or the number of waves that there is in 1 meter. For example, I remind you that you used in infrared spectroscopy the term centimeters to the -1. That means how many waves there are in 1 centimeter. In properties of time we mentioned period, but maybe a more famous or more common magnitude is frequency, in which is is represented by the letter nu, a Greek letter, and it's the inverse of the period. And what is its meaning? Its meaning is the number of waves in 1 second, and the units is second to the -1, or more commonly known as hertz. it would look like these two properties are separated from each other, but they're not. They're not because they are related through the speed of light, which is a constant. In other words, if in your light the wavelength or the wave number changes, it will retroactively change the period and the frequency. How? Well, the speed of light, that is in vacuum, this much, this is pretty fast. For speed, it should be distance over time. What is the distance of one wave? Is the wavelength divided by the time. What is the time? The period. Okay. Or we could use this formulation, and what you would see is that maybe it's a more common formulation using the frequency and the wavelength. So let's run an example. In this case, it's giving you different waves of light, and for that we need to remember the electromagnetic spectrum, and it's asking to rank them in decreasing frequency, decreasing wavelength, decreasing period, and decreasing wave number. First of all, we have to recall the electromagnetic spectrum. The electromagnetic spectrum, we saw the gamma rays here, then we saw there was the blue light, more to the right there was the red light, and finally here you would see the infrared. What we saw also is that going this way you would see that the frequency is increasing, and because the frequency is the inverse of the period, going to the left it means that the period is decreasing. Also, we saw that going this way the wavelength was decreasing, and because the wavelength is the inverse of the wave number, it means that the wave number going that way is increasing. So, in terms of decreasing frequency, which one is the wave that has the highest frequency? The highest frequency will be this one. So gamma rays, followed by blue light, followed by red light, followed by infrared. In decreasing wavelength, we saw that the largest wavelength would be on the infrared, so infrared followed by red light, followed by blue light, followed by gamma rays. Decreasing period. In decreasing period, the largest period will be infrared, so it'll be the same trend as wavelength. Red light, blue light, and gamma ray. And finally, the wave number up here. The largest wave number will be gamma rays followed by blue light, red light, and infrared. We will leave it here and we will practice way more so that all these four magnitudes are well settled.